Hello, welcome back to the my channel FFBMD. In the previous lecture, we have talked about the Kirchhoff's voltage rule and Kirchhoff's current rule, and also we have talked about the electrical instrument used to measure the EMF of a cell and internal resistance of a cell, and we have solved some problem related to this. Uh, in this we learn about Hindustan bridge, meter bridge and potentiometer. In some sense, potentiometer and meter bridge are equivalent, and Hindustan, these all are equivalent in solving the problem. Now today's topic is charging of a capacitor, and we will know how a capacitor is charged and what is its property, how did charge accumulate on the plate of a capacitor. So let's first define it. Charging of a capacitor. A charging of a capacitor without resistance. This is shown the circuit diagram of a capacitor connected with a cell. This is a switch S. At present it is open, and this is our capacitor. The symbol for capacitor is like this, and when it is closed, then a charge appears on the plate whose magnitude is equal to C into E, where E is the EMF and C is the capacitance of the capacitor. Here in the graph of charged capacitor and with time is shown here. This is a straight line because it takes no time to be charged on the capacitor plate. Consider a capacitor connected to a battery of EMF E through a switch S. When we close the switch, the capacitor gets charged immediately. Charging takes no time. A charge Q naught equal to C into V or C into E comes in the capacitor as soon as switch is closed, and the QT graph in this case is a straight line parallel to T axis as shown in the figure. Now the second case in which we charge the capacitor with resistance, that is charging of a capacitor with resistance. See, this is called CR circuit, and the circuit is shown in the figure. This is a EMF of battery, this is switch, and this is our capacitor, and this is a resistance. Resistance may be at any place. If there is some resistance in the circuit, charging takes some time because resistance opposes the charging or current flow in the circuit. As the capacitor charges, its potential increases and PD across resistor decreases, corresponding to decrease in current. After a long time, when the capacitor becomes fully charged, the entire potential will occur across capacitor. Entire potential will occur across capacitor, and the current becomes zero. Let at any time instant the current in the resistor is I, then by the loop rule, moving like this, we have minus IR plus E or minus Q by C equal to 0, or this implies minus dq by, because I equal to dq by dt, so minus dq by dt into R minus Q by C plus E equal to 0, or dq by dt into R equal to E minus Q by C. Hence dq by E minus Q by C equal to dt by R. Integrating above expression, we have 0 to Q, that is charge on the capacitor becomes from 0 to Q, because there is no charge on the capacitor initially, so we have taken the limit from 0 to Q, and finally the charge on capacitor becomes Q. So dq by E minus q by C equal to 0 to d dt by R. Now the value of this is log E minus q by C divided by minus 1 by C, and the limit is 0 to q equals to 1 by R t in the limit 0 to t. This implies log E minus q by C 0 to q, taking this value in this side, minus 1 by CR t minus 0, or log E minus q by C minus log E minus 0 by C, putting the value of limit, equals to minus t by CR. This implies log E minus q by C minus E, because this is 0, minus log E equals to minus t by CR, and log C minus q by C by E equals to minus t by CR. Hence log 1 minus q by CE equals to minus t by CR. Hence removing log from this side, 1 minus q by C will be equal to e to the power minus t by CR. This is the rules for mathematics, from the mathematical rule. Or 1 minus e to the power minus CR equal to q by C. We have taken this in this side and this in this side to get the value of q. So q will be equal to C into E under bracket 1 minus e to the power minus t by CR. This is equation 1. Now substituting E into C equal to q naught, that is the maximum or steady state charge on the capacitor, and RC equals to tau, capacitive time constant. This is called capacitive time constant, C into R is. In 1 we have q equal to q naught into 1 minus e to the power minus t by tau. This is equation 2. This is our equation 2. Now current can be written as I equal to dq by dt. So differentiating equation 2, d by dt q naught minus q naught e to the power minus t by tau, or this imply 0 equals to q, because q naught is constant, and q naught into e to the power minus t by tau divided by minus 1 by tau multiplied by minus 1 by tau, because we take differentiation, we are taking not integration. So q naught into 1 by tau into e to the power minus t by tau, or I equals to using the value of q naught, Ce into 1 by, and tau is equal to Rc. So 1 by Rc e to the power minus t by tau equals to now E by R e to the power minus t by tau, because C cancel, so only we are left with E by R, and E by R is the initial current on the capacitor in the circuit, or I equal to I naught e to the power minus t by tau, or where I naught equal to E by R, that is maximum current in the circuit. At t equal to 0, I equal to I naught e to the power minus 0 by tau equals to I naught. That is initially in the circuit there was a maximum current, and at t equal to infinity, I equals to I naught e to the power minus infinity by tau equals to I naught e to the power minus infinity I naught by e to the power infinity, or I equals to 0. That at after infinite time current in the circuit becomes 0. It means initially capacitor offers no resistance in the circuit, but after charging fully it offers infinite resistance. This state is called a steady state condition or a steady state circuit. Next, capacitive time constant tau. At t equal to tau, q equals to q naught into under bracket 1 minus e to the power minus tau by tau, or equals to q naught into under bracket 1 minus e to the power minus 1, or q naught into 1 minus 1 by e, and 1 by e is equal to 0.368. So so q becomes q equals to q naught into under bracket 1 minus 0.368, because 1 by value of 1 by e is 0.368, equals to q naught into 0.632. That is q becomes that is value of q is equal to 0.632 into q naught. Similarly, at t equal to tau, I equal to I naught into e to the power minus tau by tau, I naught e to the power minus 1, or I equals to I naught by e equals to 0.368 I naught. Therefore, time constant is the time. From this relation we can define time constant. Therefore, time constant is a time in which charge on capacitor grows to 0.6 through 32 times the maximum charge, or current decreases to 0.368 times the maximum current, and this is shown in the figure, because our the graph of charge on capacitor with time is looks like this. This is exponential graph, and it is, and current is on the current on the capacitor in the circuit also it is exponential. Now we see that at when t equal to tau, this is the point where t equal to tau, the value of q is 0.632 q naught. That is maximum q naught is the maximum value of charge, and it becomes 0.632 of q naught. Similarly, in this case, at t equal to tau, initially current was maximum, but at time passes, current decreases to 0, and at t equal to tau, it value remains 0.368 I naught. That is 0.368 of I naught. Now, potential of capacitor. We know that potential is given by V equals to Q by C, where C is the capacitance of the capacitor, or equals to Q naught by C into 1 minus e to the power t by tau, or V equals to, now Q naught by C can be written as E, that is EMF of the cell, or 1 minus e to the power minus t by tau, where E equal to Q naught by C, or V max equal to E Q naught by C. This is the maximum value of voltage on the capacitor, or potential difference between the capacitor, you can also ask. Now, energy is stored in capacitor. We have formula for energy. Potential energy is stored in capacitor, U equal to 1 by 2 CV square, that is electric potential energy, or 1 by 2 C into, using the value of C, V, we have value of V is E, is this value, and E into 1 minus e to the power minus t by tau to the whole square, or 1 by C E square into 1 minus e to the power minus t by tau to the whole square, or U equals to U naught into 1 minus e to the power minus t by tau to the whole square, where U naught is the maximum potential energy in the capacitor, whose value is U max is given by 1 by 2 C into E square. So, different value have been calculated in the case of CR circuit, capacitor resistance circuit, and these values are here summarized. That is, charge on a capacitor at any time is given by Q naught into 1 minus e to the power minus t by tau. Similarly, current in the circuit, CR circuit, at any time is given by I naught into e to the power minus t by tau. And potential difference between capacitor plate is given by E into 1 minus e to the power minus t by tau, and potential energy of the capacitor U naught into 1 minus e to the power minus t by tau square. So these are the values. Now next is potential difference across resistance. We know that the potential difference is given as V equal to IR. So VR equal to I into R. Now I value is at time t is I naught into e to the power minus t by tau into R. So this equals to I naught into R into e to the power minus t by tau. and I naught into R is equal to E. So VR equals to E into e to the power minus t by tau. The value of heat released through resistance R is given by delta H equals to I square R into delta T, or dH equal to I square R dt, or H integration T1 to T2 dH, or T1 to T2 I naught e to the power minus t by tau to the whole square R dt. Now it is integration of I naught square into R into integration T1 T2 e to the power minus 2 into 2 T by tau into dt. The value of heat released during the time the capacitor gets fully charged is given by H equals to I naught square R 0 to infinity e to the power minus 2t by tau into dt. Here time is taken infinity because capacitor becomes fully charged after infinite time. So I naught square into R into e to the power minus 2t by tau divided by minus 2 by tau by the integration rule, or using taking constant value out of bracket, minus I naught square R tau by 2 into e to the power minus 2t by tau in the limit 0 to infinity. So putting the limit, we get minus I naught square R tau by 2 0 minus 1, the value of when we put infinite value then it will be 0, and when we put 0 value it will be 1. So equals to I naught square R tau by 2, or E by I naught is equal to E by R. So E by R to the whole square into R by 2 into tau is equal to RC, and solving we get 1 by 2 CE square. So the value of heat released during the time in which capacitor becomes fully charged is given by 1 by 2 CE square. From above it is clear that the value of the heat released through the resistance is independent of the value of R resistance and has the fixed value given by this value 1 by 2 CE square. Next, the value of energy supplied by the cell or the work done by the cell is given by W cell equals to Q into E, or Q naught into E under bracket 1 minus e to the power minus t by tau, or equals to CE square into 1 minus e to the power minus t by tau. This is the work done by cell at any instant of time t. When capacitor gets fully charged, that is at t equal to infinity, W cell equals to CE square, and this is the work done by cell when capacitor gets fully charged. Now second method, we can also use second method. W cell is equal to the heat released plus potential energy stored in the capacitor. So 1 by 2 CE square plus 1 by 2 CE square equal to CE square. Next value, the value of charging efficiency is given by eta. It is called charging efficiency equals to useful energy by energy supplied, because useful energy we get 1 by 2 CE square, that is potential energy in the capacitor, and energy supplied is that is work done by cell is CE square, which is energy supplied. So CE square into 100 equal to 50%. So we have found different value, and we have discussed the CR circuit and their different importance in this topic. Now in next topic we will discuss about the discharging of capacitor.